In this lecture, we will discuss about the purification of colloid as well as property of colloid. So in purification of colloid, you can use three methods, which is dialysis, electrodialysis, and ultrafiltration. So before we go into the purification method of colloids, so first, why we need to purify colloids? In many lyophobic colloids, it contains some material in the dispersed phase, which may be undesirable for a number of reasons. For example, when they have some electrolyte as the impurity, and once the electrolyte can neutralize the charge on the surface of colloid, and it can cause flocculation of the solution. Therefore, these colloids need to be purified before it can put for further use. So how to purify colloids? You can use three methods, which is dialysis, electrodialysis, and ultrafiltration. So for dialysis methods, we use a semi-permeable membrane. Semi-permeable membrane with distilled water. Okay, and the impure colloidal solution inside this bag. Okay, and let's say the orange color particles is the impurities. Alright, so with a certain size of the semi-permeable membranes, these impurities can actually diffuse out from the colloidal solution into the bulk of the distilled water. Okay, due to concentration gradient. Okay, so this is another schematic representation of dialysis method. Let's say this is the semi-permeable membrane, and you have the colloidal particle as a bigger particle as compared to the impurity. So this impurity can actually move out into the part B. Okay, and as long as you can change the distilled water in part B, okay, the impurity can constantly move out, and then you will obtain a pure colloidal solution in part A. Okay, so in short, dialysis is the removal of soluble impurities from solution by the use of semi-permeable membrane, depending on the size of the impurity, and it is the separation of smaller molecule from the larger one, okay, from the colloidal particle in a solution by selective diffusion through a semi-permeable membrane. For example, ion can move through the membrane, but larger colloidal particles can't pass through. Okay, the impurities slowly diffuse out of the bag, leaving behind pure colloidal solution, and the distilled water is changed frequently to avoid accumulation of the impurity. Otherwise, they may start to diffuse back into the bag. And in this case, you can use heating or stirring to speed up the process, because dialysis is a passive process. It may be slow. So since the ordinary process of dialysis is slow, to increase the process of purification, we can actually apply the electrical field, okay, which is called electrodialysis. Electrodialysis is the removal of soluble impurities, again by using semi-permeable membrane, but in the presence of electrical field. So this is an example of electrical dialysis. They have three compartment vessels with electrode in the outer compartment. Okay, electrode. Okay, and application of potential cause the cation to migrate to the negative electrode. Cation move here. Okay, and the anion move to the positive electrode. So let's say you have the cation and anion as impurity. It will actually attract, okay, the cation and anion towards the electrode. In both sides you have running water. Okay, so water in here, water out here. So in that case, you constantly change the water. So By the assistance of the electric field, so these impurity particle can move through the semi-permeable membrane and purify the solution inside the center compartment. So the third method to purify colloid is ultrafiltration. So in this case, the colloidal solution are purified by carrying out filtration method using a special ultrafilter. Okay, and in this case, we apply pressure or suctions to the solvent and small particle to force them through a membrane while colloidal particles are actually retained. Okay, and in this case, because we use the force, so the membrane must be supported in a sintered glass to prevent rupture due to the high pressure. Okay, pore size of the membrane can be increased by soaking in the filter in a solvent that causes swelling of the filter. Okay, so example, cellophane swell in zinc chloride. Okay, and colloidon actually is a nitrocellulose. They can swell in alcohol. So before you use these two filters, you can soak them in the corresponding solvents before you can perform the ultrafiltration. So this is the example of ultrafiltration. Okay, here is the membrane. All right, and this one is the colloid solution. Okay, and this is a big one, colloidal particles. Okay, and the small one is impurity. So the small particles can actually move out after you apply a certain pressure, and they will force through the filter and go to another compartment, and this compartment again will collect the impurity. Then you will have a purer colloidal solution at the end. Okay, and this is another representation where they have a colloidal solution. Okay, and they apply the force from here. Okay, and whatever filter out is the unwanted impurities solution. Okay,
Purification of colloidal solutions. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. The purification of colloidal solution can be done by following methods. Dialysis. It is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. The apparatus used for this purpose is called dialyzer. Electrodialysis. The process of dialysis is quite slow. It can be made faster by applying an electric field if the dissolved substance in the impure colloidal solution is only an electrolyte. Then the process is known as electrodialysis. Ultrafiltration. In this method, colloidal solutions are purified by carrying out filtration through special type of graded filters called ultrafilters. These filter papers allow the electrolytes to pass through them but do not allow colloidal particles.
so in real life, the purification of colloid can be seen in artificial kidney machine, whereby because patient blood is a type of colloid, right? Okay, so patient blood can pass through a semi-permeable membrane, okay, for hemodialysis. Okay, and cellophane pass through the urea, glucose, electrolyte, but they won't pass through the plasma protein, which is bigger in size. all right, and also blood cell. So the pure dialyzed blood enter the body again through a vein. Okay, so success of the artificial kidney machine depend on its ability to reduce the blood urea, which is our impurities. Okay, and the cellophane coil are supported on a drum rotating in the electrolyte solution, which is what you call a rinsing solutions. Okay, and here the bloods go out from here, okay, and it pump through and go through anticoagulant so that the blood doesn't clot, okay, and then they go to the dialyzer with the semi-permeable membrane, okay, after they have excrete or diffuse out the urea, glucose and any unwanted impurities, okay, it will pump back to a vein and back to the body. So in artificial kidney machine, it is important that the rinsing solution should have a certain criteria. For example, the substance that present in excess in the blood, which is unwanted, for example urea, should diffuse from the blood to the rinsing solutions. And substances which are deficient in the blood, for example bicarb, should be available in the rinsing solution, so they will diffuse from the rinsing solution to back to the blood. And substances which are present in normal amount in blood are kept unaltered, have the same concentration in both blood and rinsing solution. Okay, meaning that in the rinsing solution, that's one here, rinsing solution, and here's the blood. All right, so we will expect the blood they have urea, but the rinsing solution they do not have urea. And the blood you have deficient in bicarb, and you have some amount of bicarb which is higher than the blood, so they can diffuse into the blood. Or anything that is, for example, you have sodium here and you have sodium that you want to maintain both sides the same, then you should actually have your solution in the right isotonicity to the blood, so that it won't diffuse in and out between the blood and the rinsing solution. So after we have finished the purification of colloids, let's go into the properties of colloids. So there are three main properties of colloids, which is related to kinetic, optical as well as electrical. For this particular lecture, I will only focus on the kinetic and optical. So there are 6 kinetic properties of colloid, which include Brownian motion, diffusion, sedimentation, osmotic pressure, the donor membrane effects, as well as viscosity. And we'll go into each properties in more detail. So first, Brownian motion. Colloidal particles are subject to random collisions with molecules of the dispersed medium. To each particle move in regular and complicated zigzag pathway. It is first observed by Robert Brown with pollen grains suspended in water. And the velocity of the particle will increase with decreasing particle size and their own viscosity. Increasing the viscosity of the dispersed medium, of course it will become more viscous, so the movement will reduce, hence reduce the Brownian motion.
Hazard motion can also be observed when small colloidal particles suspended in a liquid are examined under a powerful microscope. The zigzag motion is due to unequal bombardment between the suspended particles and the molecules of the surrounding medium. This irregular motion of suspended particles is referred to as Brownian motion. We shall now study movements of large and small particles suspended in liquids. Let us first look at an isolated large particle A suspended in a solution. A number of molecules hit particle A from all sides. On an average, the impact mutually cancels out. So, the resultant force on the particle is zero. Now, observe the particle B, which is very small. Particle B is hit by less number of molecules. Moreover, it is not hit equally from all sides. Due to this, there is a resultant force. This resultant force alters the direction of particle B. When particle B moves, the direction of the resultant force also changes, resulting in a zigzag motion.
So next is diffusion. As a result of Brownian motions, the particle diffuse from a region of higher concentrations with one with lower to one with lower concentrations. And the rate of diffusion can be expressed by the fixed first law, okay, where the dm is the mass of the substance, diffuse at time dt across an area of A under the influence of concentration gradient, which is this one is the gradient, okay, and this is a diffusion constant, okay, and the minus denote that the diffusion takes place in the direction of decreasing the concentrations. The third kinetic properties of colloid is sedimentation. Small particles, let's say if they are less than 0.5 micrometer, they tend to have Brownian motions. Okay, when they have Brownian motion, they have significant zigzag pathway movement, and they tend to prevent sedimentation due to the gravity, and they will promote mixing instead. So please recall back that colloid solution, they have kinetic property of Brownian motions. So meaning that they might not be able to sediment under gravity. So in that case, for a colloidal solution, we need to use an ultracentrifuge, which provide stronger force to promote sedimentation in a measurable manner. Okay, in that case, kind of sedimentation of colloid is possible. So in that case, according to Stokes' law, sedimentation of colloid under ultracentrifuge will follow Stokes' law, okay, where V is the velocity of the sedimentation spherical particles, ρ is density, and ρ naught is the density of medium, and N is viscosity of the medium, and G is the acceleration due to gravity. However, if we use ultracentrifuge, so the acceleration is due to the ultracentrifuge machine. Okay, so the fourth kinetic properties of colloid is osmotic pressure. As the colloid are solute, they can actually contribute to the total osmotic of a solution. So let's say in plasma, the plasma protein are major colloid particles present. So in plasma, actually the oncotic pressure is only about 0.5% of the total osmotic pressure of a normal colloid solutions. Okay, however, the 0.5% is enough to keep the blood inside the vascular. So the fifth properties of colloids is the Donan membrane effect. And the definition of it is diffusion of small ion through the membrane will actually be affected by the presence of a charged macromolecule that can't penetrate the membrane due to size. So the charged macromolecule usually is the colloidal particles. Okay, and let us look at the video to understand further.
The Gibbs-Donan equilibrium is a phenomenon of solutions that contributes to the formation of an electrical charge across a cell membrane. The Gibbs-Donan equilibrium can be illustrated using a beaker separated into two chambers by a semi-permeable membrane. A solution containing potassium chloride is added to side 1 of the beaker, and distilled water is added to side 2. The membrane is completely permeable to both the potassium and the chloride ions. Initially, the potassium and chloride ions diffuse passively through the membrane from their high concentrations on side 1 to their lower concentrations on side 2. The ions continue to diffuse back and forth between sides 1 and 2 until an equilibrium is attained and equal concentrations of the potassium and the chloride ions occur on both sides of the membrane. At equilibrium, equal numbers of both ions move back and forth from one side to the other to maintain both equal concentrations of ions and electrical neutrality on each side of the membrane. However, the system becomes more complicated if an ion is present on one side of the membrane that is not permeable to the membrane. In this illustration, PR represents anionic protein, an impermeable anion common in cells. Potassium ions and chloride ions easily penetrate the membrane, separating the two chambers. The impermeable protein anion is retained on side 1. As we shall see in the next scene, the presence of an impermeable ion on one side of a semi-permeable membrane has profound effects on the final distribution of permeable ions as they diffuse to an equilibrium in the solution. An unstable situation develops when a solution with an impermeable anion is placed on one side of a semi-permeable membrane and a solution of permeable ions is present on the other side of the membrane. In this example, side 1 is a solution of potassium cations combined with an impermeable anion such as an anionic protein. Side 2 is a solution of potassium and chloride ions in concentrations that are equimolar with the ions on side 1. Since side 1 does not contain chloride ions diffuse along a concentration gradient from side 2 to side 1. The presence of both negative chloride ions plus impermeable anions on side 1 makes side 1 negative relative to side 2 and establishes an electrical potential difference across the membrane between sides 1 and 2. Development of the negative charge on side 1 counterbalances the concentration gradient for chloride ions and prevents chloride concentrations from becoming equal on both sides of the membrane. At the same time, the negative charge on side 1 attracts the positive potassium ions to migrate from side 2 to side 1 along an electrical gradient. The potassium ion concentration on side 1 now exceeds that on side 2, and potassium ions will diffuse back from side 1 to side 2 along a concentration gradient. At equilibrium, the competing electrical and concentration gradients for each ion are in balance, and there is no net flow of ions through the membrane. Potassium ions and chloride ions move back and forth between sides 1 and 2 in response to the competing electrochemical gradients, so that each side remains electrically neutral within itself due to equimolar concentrations of both cations and anions. Between the two sides, there is an unequal distribution of the permeable ions with more total negative anions on side 1. This imbalance in the distribution of permeable ions results in an electrical charge across the membrane. The side of the membrane with the permeable cations and anions is positive relative to the side with the impermeable anions. The voltage gradient across the membrane at which an ion is in equilibrium with its diffusion gradient is called the equilibrium potential and is calculated by the Nernst equation.
So the application of donor membrane effects is actually facilitate the absorption of ionizable drugs from gastrointestinal tract by co-administered macromolecule of the same charge, so they can have the mutual ionic repulsions. So example, when we can co-administer macromolecule, for example CMC, carboxyl metacellulose, plus a diffusible anion, potassium benzyl penicillin, so to enhance the diffusion of the antibiotic to cross the membrane. So the last kinetic properties of colloid is viscosity. So viscosity is the resistance to flow of a system under an applied pressure. So in viscosity of colloid, it allows the calculation of molecular weight, okay, and it provides useful information about the shape of colloidal particle. For example, when you have the colloidal particle which is spherical in shape, they have relatively low viscosity, and when you have a colloidal which is linear, okay, they have a relatively high viscosity, because if the linear colloidal coil up into sphere, the viscosity of the system fall due to the change of the shape. Okay, and the high viscosity of the linear colloidal is because the long particle cling together, thereby they form a network within the solvent, so they prevent the movement of each other and they cause resistance to flow, so it increases the viscosity. So globular particle can pass each other much easier, that's why the spherical particle has lower viscosity. So we have finished with the kinetics properties of colloids, and now let's go into the optical property of colloids. So there are three optical properties of colloid, whereby colloid is visible because of its Tyndall effects, okay, and besides, it is also visible under ultra microscope. And the last one is it is visible under electron microscope. The Tyndall effect is the light scattering properties of colloids. It names after John Tyndall, which means the effect is caused by a reflection of light by a very small colloidal particle in a transparent medium. So true solutions do not scatter light and they look clear. However, colloidal dispersion they contain opaque particles that they do scatter light and they will appear turbid. So when a strong beam of light is passed through perpendicularly to two solutions, for example, the one is true solution and one is colloidal solutions, and placed against the dark background, the path light of the beam is not visible in the true solution. However, the path light of the beam is visible in the case of colloidal solutions, meaning that the light is being scattered. So furthermore, the path light is forming a shadow at the dark background, and the illuminated beam or cone formed by the solution particle is called tinder beam or tinder cone. The tinder effect actually explains why the sky is blue and why the light transmitted to the earth is yellow or red.
Let us study about Tyndall effect. Tyndall effect is a phenomenon in which a beam of light scatters on striking the particles present in its path. This scattering of light is responsible for the blue color of the sky. We know that our atmosphere primarily consists of oxygen and nitrogen particles, along with dust, smoke, and other particles in comparatively smaller proportions. The size of these particles in the atmosphere is responsible for the color of scattered light. When the sunlight strikes particles of dust, smoke, etc., which are bigger than the wavelength of sunlight, all the colors of sunlight are equally scattered. As a result, the scattered light appears white. However, when the sunlight strikes particles of oxygen and nitrogen, which are smaller than the wavelength of sunlight, the colors of sunlight having shorter wavelengths, that is, blue and violet, are much more scattered than colors having longer wavelengths. But our eyes are much more sensitive to blue color as compared to violet. Hence, the sky appears blue to us.
The knowledge of tinder effect is important for the measurement of particle size estimation, particle shape, and particle interaction estimation in a colloidal solution. So the second optical properties of colloid is it is able to be seen under ultra microscope, and it appears as a spot of light against the dark background of the microscope. It can be used in the technique of microelectrophoresis for the measuring particle charge. Besides, colloidal particle can also be visible under electron microscope, and it will give an actual picture of the particles up to 5 angstroms and used to observe the size, shape, and structure of the solutions. And high energy electron beams are used for greater resolving power. However, the only disadvantage of the electron microscope is only dry sample can be examined, and they cannot give any information on the solvations. And this is the example of optical image from ultra microscope as well as from the electron microscope. With that, I end the current lectures and keep the electrical properties of colloid in the next lecture. See you.